You do?
We'll be set for next time.
Let's see. Is it a
Is
good question? It's a tough one. I didn't say that.
French out, we'll just get like a hot sauce.
Oh, you got your math logo.
Yeah, we look at the important piece of paper.
Yeah.
Where is your answer?
Oh. Yeah,
No one
that's-
knows it.
we'll just get all this
That's your
tattoo.
math logo.
I think we can do this.
Do you know that? That's math.
I would
That's
probably get like
square root
a
of an
Pythagorean
AS.
identities on there or something.
Here, all of them. No, you gotta
Every
get all
single
of them.
trick identity is just all over your arm. It's like an order.
Yeah,
If you
it's
get.
because a square root
No,
is radical.
No.
Yeah.
You know those tattoo machines that are. Not really.
All right, where's your question?
Just like turn it on.
It's so dumb, but
No, the ones that stay on for like 2 weeks and come off.
Yeah, those would be.
so like how do I figure out?
Yeah, we're gonna create a new standard in
So
college.
you have to
Trust the US
eliminate
man
one
because
by
that's
one.
the smartest idea to do this. You go, oh, shit, we should do that.
But we don't know until we try it. We don't know.
Yeah, let's ruin it for everyone else.
Yeah, I mean, you already do that for us.
I can't multiply this by 3, and add the C's will not add. And then you have two AB equations.
Seatbelts are.
All right, so today we are starting.
No, I should be alone.
Silence, silence.
Order in the court.
The topic today, improper integration. This is the beginning of getting into the very abstract nature of Calculus 2. We are going to, this is sort of the precursor to infinite series. And if you look at the image up here on the board, we see a curve that has an unbounded tail. So if we look under this curve, this tail is unbounded because that area goes on forever and ever and ever and ever. That doesn't necessarily mean that the tail's area is infinite, but it goes on forever and ever. So we want to distinguish between those two words. If somebody says something has infinite area, that's different than bounded and finite area. So first question, is it possible, keep this to yourself if you already know the answer, can you add an infinite number of positive numbers together and get a finite result?
Yes.
I say keep it to yourself, clown! Look, I got to throw something. I mean, where are these nice clean rags? I might have to stuff that in your mouth. Does everyone agree with that? Or is your instinct, most people's instinct is no, you can't add an infinite number of positive numbers and get a finite result. And that's most people's instinct. Somebody other than Austin, can you give me an example of adding an infinite number of positive numbers together and getting a finite result? Fractions, like?
Like if you had like 1/9, and then you could do like 1/100. Like I guess I'll do it like 1/10 and then 100.
Yep.
And then 1,000.
Yep, exactly. So this is an infinite collection of positive numbers that we can add together, and that will be finite. This is going to end up being 0.1 repeating, which brings up another question. The typical example I show first is usually this one because we know what the fraction is instantaneously. If we add those together, what do we get? 0.3 plus 0.03, etc. We get a third, right? So it is possible. So we want to make sure that's clear in our mind that you can add an infinite collection of positive numbers together and get a finite result. The key is that these numbers have to be going to 0, but not only do they have to go to 0, here is a classic example that we will see a lot this semester. This is called the harmonic series. And the harmonic series diverges. In other words, the sum of that is infinite. So it's not enough that the terms are going to 0. They have to go to 0 pretty quickly. So they have to go to 0 fast in order to keep the sum from inflating to infinity.
Okay, so this slope has to be steep enough in order for it not to equal infinity?
Yes, exactly. So they have to be going to 0, and they have to be going to 0 at a reasonable clip. in order to have something finite. So let me ask you a simple algebra question that used to be taught in all algebra courses, but isn't always taught that way anymore. What is the rational expression for 0.1 bar? How do we turn that into a fraction of integers? Did I hear a 9?
I said 1 9. That's what I was gonna say.
Do you know how to do it?
1 9.
That's how we would write it, yes. So the math behind it is this. So if we set this up, we can say that x is equal to that. Then if we, I moved my decimal point. I was thinking ahead there. I don't want to move it quite yet. So if we let x equal the repeating decimal, and then we multiply both sides by 10, that's going to do this. And that still is repeating. That hasn't changed. But you can separate this and write this as 1 plus 0.11, blah, 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 repeating. And what is 0.1 repeating? Well, that's what we let x be originally. So this is going to tell us that that's 10x. Let's move this stuff down. So we have 10x is equal to 1 plus x. Is everyone following that? 0.1 repeating, that's what x is. That's what we originally let x equal. So then we subtract off the x from both sides. We get 9x equals 1. And that brings us to x equals 1 over 9. So that's the way that you should have learned it back in Algebra 2, back in the day, or even before Algebra 2, Algebra 1 even. So that's how you turn a repeating decimal into, because you know a repeating decimal is rational, so you should be able to write it as a ratio. That's how we would do it. All right? Okay. So, that said, that gives us this idea that you can add up a big collection of positive numbers, an infinite collection of positive numbers, and get a finite result. So that leads us to this improper integral right here. And it's improper because the domain is not a bounded interval. So when we hear the word bounded in math, think you just can draw a circle around it. Like an interval is bounded because you can draw a circle around it. If you're going from 0 to infinity, well, I guess that's an interval. You can't draw a circle around the tail of this. But like an interval from A to B is bounded. You can put a circle around it. But you can't do that here. This goes on forever. And we often think of area under the curve as a sum of rectangles. And now we know that, oh, well, if the rectangles have these areas, that unbounded area could in fact be finite. That unbounded area can have like finite area. Okay? So, here is how we are going to do this. When we look at this improper integral, so we're going from a to infinity, that's improper. We know it's an unbounded region. What we're going to do is chop up the region and first create a definite integral. So integral a to b is definite, right? We've got finite limits of integration. And then we're just going to let the b go off to infinity. So when we create this definite integral, this is going to turn into a function of b. And then we will take the limit as b goes to infinity. And that will be how we compute that area. The area could be infinite or it could be finite. We're going to have to explore it. If we have it set up so that the tail is a left tail, same idea. We take our improper integral. We're going to create a definite integral. And in this case, we're going to let a go to infinity. So we're first going to create a definite integral that's going to find that area, and it's going to find that area as a function of a. So this will be a function of a. And then we take the limit as a goes to a negative infinity. And that'll find it. That'll find the area. If we have a wonky situation where we have a bell curve, we have two tails, you can't just integrate from negative infinity to infinity and make it negative a to a. That won't work. You have to chop it in half and do two separate integrals. So you would have to do this left side, and you'd have to do this right side. You can split it anywhere you want, create two impropers, and do each one individually, and then add them together.
Do we have to remember our limit rules?
Oh,
What do you think?
you said no.
I don't want to-
Yes, you definitely need to know your limit rules. Yes, you absolutely need to know your limit rules. We'll go over them for sure. We'll do a bunch of examples. And we're only using the most intuitive ones. We're not going to be doing anything crazy like rationalize the numerator and then, do something goofy. We're going to look at mostly pretty common limit rules. So let's try one of these. Let me also point out that these pictures are of horizontally unbounded regions. We can also have vertically unbounded regions, vertical asymptote. So these first ones are going to be horizontally unbounded. Ari?
Can you know whether or not an integral would have finite or infinite area just by looking at it?
No.
Okay.
Yeah, you can't look at it and tell. Yeah. You get an idea. And we'll see as we look at these pictures, some of them you'll see that the tail is going down really fast. Like that looks like it's going down pretty fast. And some that are going to be looking like they're going really slow, and it's going to be like, oh, that's probably going to diverge. It's not going to go fast enough. So you can get an idea, but you definitely can't tell for sure. But we'll come up with some rules that help to clarify when you should expect convergence and when you should expect divergence. So the first function we're looking at is 1 over x squared. From 1 to infinity. So we want to integrate that from 1 to infinity. So the first thing that we are going to do is create a definite integral and take the limit of it. So we are going to integrate from 1 to b and then take the limit as b goes to infinity. So we'll write this as x to the negative 2 dx. And so this should be, hopefully this is clear by now. We've talked about this a little bit. So the integral here, because we have a letter up there in that top position, that means that this is not a number, this is a function. The definite integral where you have numerical limits is always a number, but if you have a variable up in either position, this is going to be a function. So this is going to be a function of b, and then we're going to take the limit of that function. And then we'll get a number. So let's go through the math. So we know that the integral of this is x to the minus 1 divided by minus 1. And that's going to go from 1 to b. So we'll have the limit. The minus 1 down here, we could write this as minus 1 over x. So that's going to be minus 1 over b. Minus a minus is plus. 1 over 1 is 1. So this whole thing is going to simplify to that. And the limit is as b goes to infinity. And you don't have to write the b goes to infinity every single step. Once you've done it the first time, you can wait till the last step to do it again.
So we don't need to in the middle step.
Yeah, you don't need to put this part in. Once you've established what the limit is, you don't have to keep writing it.
Okay.
Usually I'll write it at the end at the last step. And what does that limit equal to? 1. So this tells us that this area is finite, and the area under the curve is 1. It's exactly 1 unit. Not approximately 1, it's exactly 1.
It's crazy.
I know, right? It's totally crazy. Which brings up another interesting concept. The decimal form of numbers is not unique. This area is 1, and you might think to yourself, well, how do we write that as like a sum of rectangles? And the answer is like this. This number right here, also known as 0.9 repeating, that is also identically equal to 1.0. 0.9 repeating is the same as 1. Decimal representations of numbers are not unique. So you can write 0.9 bar, it's the same number as 1. Those are the same. If they weren't the same, there would have to be a positive distance between them. And we can show that there is no positive difference between the two. If you say the difference is point with 100 zeros and a 1, I can say, no, it's not, and show you that it's not. So you can prove pretty easily that these are the same, just different looks. Okay, so in our mind, we now know 1 over x squared, that's going to go to 0 fast enough to get convergence. 1 over x squared is steep enough. Double diamond, nice and steep. Double diamond will go to 0 fast enough that we have finite area.
Why is 0.9 repeating equal to 1? Is that technically slightly off?
Nope. How far off is it? What do you mean by slight?
Almost infinitesimally small.
They are identically the same, because this goes on forever and ever and ever. So if you assume that they're different, then there has to be a positive difference between them. If you have 2 distinct points, there's a measurable distance between them.
Okay.
And there is no measurable difference between those.
Okay.
Because that can get as accurate as you need. Any measuring tool you use, you can make that even more accurate. Because that's going to go on forever. So they're the same.
It was like 1.9 repeating. Would it be the same
As
as
2.
2.9?
Yep. 1.9 repeating is the same as 2. Yeah. Dave?
What if that integral was from 0 to infinity? And then
So 0 to infinity is a little different because this would have a vertical asymptote also.
Yeah.
So we would have to split it and do this part and then do the vertical part.
Oh, okay.
So we'll do the vertical ones in a minute after we finish the horizontal ones. The horizontal ones are more intuitive. The horizontal ones are really obvious. When you see the infinity symbol in the limit of integration there, you know instantly that it's improper. Right? We know instantly. When we have a vertical unbounded region, it's not as obvious. We'll see why.
Why are they called improper?
Because you learn definite integrals to find the area beneath a curve, and this just feels improper because it's not intuitive that the area under this curve is finite, and it's not necessarily finite. So it's improper in that sense, that this area could be infinite, might not be infinite, could be finite. So it's just, definite integrals are sort of very proper. We're going to integrate from 1 to 5. Now we're saying, hey, let's integrate from 1 to infinity. That's improper. That's like going crazy, asking crazy questions. All right, so let's try this one. So we have an exponential function here, 2 to the negative x, and once again we're going to integrate from 1, so 1 to infinity, all this stuff out here, and just by looking at this picture and using some intuition, we've already seen that 1 over x squared goes to 0 fast enough for convergence of the area. So an exponential, yeah, that's got to be finite, intuitively. Because an exponential is going to go to 0 faster, right, than any polynomial.
So if we're given like different problems like this, do we have to just think of what it would look like?
If you don't have the graph given to you,
If it's like to tell if it's finite or not, or is there a certain
we have to do the math to figure out whether it's finite or not. But intuitively, if we have a graph of it, if we see an exponential, intuitively that's going to go to 0 really fast. So we're going to try to set up, we call it a, we have a chart that we're going to come up with called the growth rate chart. Which functions grow the fastest, which functions go to zero the fastest. And so we're going to try to set up an intuition for that as we go. So right now we have 1 over x squared goes to 0 fast enough that we get convergence. An exponential grows faster than a polynomial, so 1 over an exponential is going to go to 0 faster than a polynomial. So yeah, we'll get to that. All right, so let's integrate this. So the first thing we do, we obviously see that infinity symbol right there. The second you see that infinity symbol, you should be writing down the word limit. That's the first step. You have to use a limit. So you're going to take the limit as b goes to infinity of integral 1 to b 2 to the negative x dx. Okay, so integrating an exponential, what is the antiderivative for an exponential? So, and this is the one, I didn't need to rewrite that again, I've already established it. But okay, so the integral of an exponential, is itself, always the first step, whether it's the natural exponential, e to the x, whether it's another base, the first step is always itself. We also always know that we're going to have to use the chain rule, so we're going to have to multiply by a -1. And then the third piece of the puzzle is this is not a base e. If it's not a base e, you need a modifier, and that modifier is natural log. Do we multiply by it or divide by it? I hear multiply. That's the derivative.
Oh.
But if you're integrating, you're going to correct it by doing this. So let's go back to Calc 1 for a moment just as a refresher. If you had the function y equals 2 to the x, and you wanted to take its derivative, if that was your goal, the question is, how do you do that? Well, the idea is that you take the derivative with respect to x of both sides of the equation. So you're going to take the derivative with respect to x of y, and you want the derivative with respect to x of the other side. Eesh. Why is it so temperamental today? And when you are right here, this is the part that we don't know off the top of our head. So in Calc 1, you learned a technique called... Well, you learned chain rule, but this isn't chain rule.
Log properties.
Log properties.
Implicit
Log
differentiation.
differentiation. Log diff. Log diff. So we're going to start with our original, and we're going to take the log of both sides. Whoops, that's supposed to be a 2. So we take the log of both sides. And when you take the log of both sides, the x can come down using the power rule for logarithms. Because this piece we don't know. We don't know how to take the derivative. Oh my gosh, this board. Don't know how to take the derivative of that yet. So we come up to our original, take the natural log of both sides. Now we do this derivative of both sides, bless you, with respect to x. So we're going to take the derivative of both sides with respect to x, whole equation. On the left side, the derivative here is 1 over the inside times the derivative of the inside. Well, the short notation for the derivative of the inside is y prime. On the right-hand side, what is the derivative of that with respect to x?
ln2.
Just ln2. It's a linear function. So there we have it. And our whole goal was to find y prime. So that's going to be natural log of 2 times y. Well, we said that y was equal to 2 to the x. So we end up with natural log of 2 times 2 to the x. So the derivative, we have that. So when you differentiate an exponential, you have this extra correction factor multiplied by the log of the base. Even with e, it works because the log of e is 1. So it works there also. All right, so let's get back and we can double check that division is the right thing to do in a moment. So let's keep going here. So we had limits from 1 to b. If you want, sometimes evaluating the limit is easier if you get rid of all the constants. So we could clean this up a little bit and factor out the -1 over natural log of 2 if we wanted. We wanted to just look at the root of this exponential. So it's going to be 2 to the negative b minus 2 to the -1. So I factored out the negative divided by natural log of 2. That all came out to the front. So all that we have left is 2 to the negative x. Plug in the b, plug in the 1. We have that. Now here's another choice that you have to make. Many of you can see that that's exponential decay and understand the limit really easily. A lot of people get flustered trying to evaluate limits with negative exponents. So if you want, you can rewrite this in a way without negative exponents. For a lot of people, it's a lot easier. Doesn't matter to me, whatever works for you. So now it's really obvious that that first fraction goes to 0 because the denominator is exploding, so the fractions are shrinking to 0. So that first fraction is going to 0. That thing is going to 0. So that tells us then that the overall limit is -1/2. The limit of a constant is itself. So -1/2 times this over here, that should be an ln of 2, and that's going to give us 1 over 2 natural log of 2. So this is the area underneath that curve. So it is in fact finite.
Infinite perimeter.
Infinite perimeter. There is no perimeter actually. Perimeter means that you have, if you have the
length.
If you have the perimeter around an, a region, then that region has to be finite area by definition. Perimeter is, this has no perimeter because this never touches.
So then infinite length at that point.
Yeah, so it's unbounded. We'd say unbounded. All right, so that is our process. That is the process.
Trick sub.
No trig sub yet. Let's try another one. So we're going to do one that's still a horizontal tail, but it's going the other way. And when you look at the graph, you can kind of see that, oh, it's tapering very slowly. You know, like those exponentials are, you know, they become indistinguishable from the axis almost instantaneously. Really quickly, they're indistinguishable. This one just sort of has the flavor of being unbounded with infinite area.
So can we just say that that one's divergent?
You can say it, but you get no credit.
Oh.
I mean, maybe I'll give you 1 point.
See, if
Well,
it's
the
not
whole point is to
divergent,
do.
but
We
made
wanted to.
logical flaws or anything like that.
But we want to be. The math is supposed to confirm our intuition. We're supposed to refine our intuition, and then the math just confirms it.
My intuition.
Like if you. You're so lucky. You're gonna be a millionaire.
He's gonna get 60 on his test.
Okay, so here
1 point for every question.
we're
I think the answer is 6.
So here we're going to the left. So the idea is that we're going to create a bounded region. So we're starting at 0, and we're going to plop A in over here somewhere. And so the first thing we're doing is finding the area of this as a function of A. So that'll be a function of A. And then we just let A go to infinity. So let's see how it plays out. So this is going to be the limit from A to 0.
You mean A is going to negative infinity?
Yep,
Okay.
negative infinity, yes. So we will rewrite this so that the exponent is in the numerator. that's how we integrate. So we have that. So this will give us limit. We'll use the power rule. So we add 1 to the exponent, get 2/3. Divide by 2/3, which means multiply by 3/2. We also have to do RCR. The derivative of this base is how much? -1, so we're also going to multiply by -1. Limits of integration are a to 0. And then we're going to plug in our limits of integration and get to a place where we can eventually evaluate this limit. So that -3/2, if we want to pull it all the way to the front, we can. Often easier just to get that constant out of the way. And that, let's see, 2 to the 2/3, 2 to the 2/3, minus the quantity 2 minus a to the 2/3. And we're taking the limit of all of that as a goes to negative infinity. Okay, so as a goes to negative infinity, this quantity in here is going to go to positive infinity. All right, 2 minus infinity, so you'll end up with a positive number, so that's going to go to positive infinity. And how about positive infinity raised to a fractional exponent?
Still infinity.
Still infinity. In your mind, you should be thinking birdwing. You're thinking about, if you think about the function y equals x to the 2/3, and we just focus on the right-hand side of it, yes, you could put negatives in here and it will come down and do this mirror thing. We don't care about that though. Over here, all these fractional exponents create these bird wings. They're all going to infinity. They may be going very slowly to infinity, but they're going to infinity. So this whole thing is still going to positive infinity over here. Okay. Now we have a positive number, 2 to the 2/3, that's positive, minus a massive number. So where is all this going?
Negative.
That's all going to negative infinity. But then we multiply by a -3/2, so the total will be positive infinity, because we have a negative times a negative here. So we say that this diverges. So therefore, the integral diverges. So if it doesn't go to a constant, we say it diverges. And
Is there a symbol for divergence?
We just say DIV usually.
Not meaning take the divergence of something, but like symbol for like that kind of.
No.
divergence?
I mean, we use this symbol for therefore, the 3 triangles, or the 3 dots means therefore. All right, so this integral diverges. The area is infinite. So however you want to think about it, infinite area, divergent integral.
And do we have to say divergence? Or can we
You can just say plus infinity. That's totally fine. Yeah, when we get to infinite series, we'll use diverge and converge all the time instead of just infinity or not.
Can we use just infinity?
Yeah.
Okay.
Yeah.
So speaking of that, do we have to write sentences because statements about why it diverges or converges?
No,
No? You think that?
not yet.
Oh, for infinite series you?
Wait, for infinite series, that's what the tests are. So we'll have to say because of whatever. The comparison test, or because of the limit comparison test, or because of. So we'll do that with series. Not with these, though. Not with these.
Don't give them ideas.
We also should never get negative in either area, right?
That's right. And you could get negative infinity for the evaluation of an integral, though, never call it area, but, you know, so if this curve was below the x-axis, you know what I mean? If it was reflected down where you sort of get signed area, but yeah, it would not be area.
It's like a vector symbol.
Oh, I see.
And, yeah, question.
So was my intuition right?
Your intuition was rock solid.
1 point.
So, 1 point out of 100. Long way to go. So, notice what the power on the denominator is. The power on the denominator is 1/3. So far we've got 2 test cases. Power of 2 in the denominator led to convergence. Power of 1/3 led to divergence.
Is it like a
so
divergence test?
we're getting there. We're getting there, yes. We're going to have a threshold that we're moving towards. Moving towards the threshold. Sounds like a movie. So here's one that is double-tailed. So it's got an unbounded left side, and it's got an unbounded right side. We have to split it and then do each side individually.
Would you do one in reverse? Like, do one like A to 0 or 0 to something, and then the other one just in reverse and add them again?
Right, and that's exactly, and it doesn't matter where we split it. Usually we split it at 0 because 0 as a limit of integration is always easier. And so we'll do what Jose just said. We'll integrate from -infinity to 0, get that area, and then integrate from 0 to infinity and get the right area, and then add them together. If either one of them is infinite, the integral is unbounded. Infinite plus finite is still infinite. Infinite plus finite is still infinite. So if one side is infinite, then you're done. And if both sides are finite, we just add them together. So let's see. So we're going to create 2 integrals. We're going to integrate first from a to 0 of the same. Fourth is so sensitive. So we're going to integrate a to 0. And then we're going to integrate from 0 to b. And what is the technique that we've used for trinomials that didn't factor?
Complete the square.
Complete the square. If that was a trinomial that factored, we would use if that PFD. If this polynomial factors, then we can use PFD. If it doesn't factor, we use completing the square. All right, so this is going to be the limit as a goes to -infinity. And we're going to have a to 0. And then when we complete the square here, we're going to have x plus 1 quantity squared. X plus 1 quantity squared plus what? 4. Plus 4. Yep, we should be seeing tangent function in our horizon. Inverse tangent function. And so then we have, for the other side, the limit is b goes to infinity. And we're going to go from 0 to b. Same exact denominator. So we get that.
Something's from above versus supposed to happen together.
Yep, we're going to add them together.
Okay.
That's what that is.
Because if you scroll a little bit, it comes up like. Sorry.
Oh, that's a plus. Yeah, thank you.
Yeah, of course.
Yeah. Thank you. All right, so now we've got something that looks like an inverse tangent. First thing we've been doing is factoring out the constant there to make it a sum of squares with a 1. Makes it easier in the long run. So let's go ahead and factor out that 4. So we have 1/4 limit integral a to 0 dx. When that 4 factors out, there's no 4 over here now, so we create one. So we get that. Same exact thing over here. No difference. So these integrands look the same. and now it's in arctan form. We don't need to do trig sub. If you did, it would still work out just fine, but you don't need trig sub. This is immediate. We have 1/4 limit. Arctangent of x plus 1 divided by 2 with, Is that quantity in the parentheses a linear function? Yep. What's the derivative of that quantity in the parentheses? 1/2. So RCR says take the derivative of the parenthetical quantity and divide by it. So if we divide by 1/2, we multiply by 2. And that's going to go from a to 0 plus 1/4 the limit. Same exact thing over here. We're going to have 2 times the arctangent of x plus 1 divided by 2 here from 0 to b. All right, any questions up to that point? Okay. So the 2 can cancel with the 2 in the denominator here, and we can have 1/2 limit. Now here I'll stick the subscript on the limit back. A is going to go to -infinity. Plug in the 0. That gives us arctan of 1/2. Arctan of 1/2 minus arctan of a plus 1 divided by 2. Parentheses, arctan b plus 1 over 2 minus arctan of 1/2. Okay, wow. Okay, wow. There's some cancellation. Don't these arctans of 1/2 cancel? One's positive, one's negative, so those cancel. Right, the limit of a constant is a constant. So this limit of a constant is just going to be itself multiplied by 1/2. Same situation over here, different signs, so those are going to cancel.
Can you even do that, granted that they're in 2 separate limits?
Yeah, you can. Limit of a constant is a constant. Limit of a constant is a constant. So let's focus on the non-constant part. What is the limit as a goes to -infinity of arctangent of all that? What is that limit going to be? That limit will be? Which is?
Negative infinity.
Nope. Yeah, almost. Negative pi over 2. So it's positive to the right, negative to the left. So if we look at that arctangent function, it looks like this. There's a horizontal asymptote at pi over 2, horizontal asymptote at negative pi over 2. So as the argument, the stuff on the inside, as that goes to infinity, negative infinity, this quantity goes to negative pi over 2. And then there's a negative in front of that. So this part in here is going to negative pi over 2. But then we multiply by -1. So we get positive pi over 2. And then we multiply by 1/2. And so we get positive pi over 4. So that's the left side. And then we go to the right side. as b goes to infinity, the inside of arctan goes to infinity, and that means x is going to infinity in this graph. The y's are going to pi over 2, so that goes to pi over 2. Once again, we multiply by the half out in front, so we get pi over 2 times 1/2, which is pi over 4. And our total limit is pi over 2. So that tells us that our area is finite. That unbounded region has finite area.
Like, I've especially noticed the last couple.
Any questions on that?
Just remember the first.
Ari, you have a question?
How would we know the horizontal asymptotes of the inverse functions?
The only ones that we really are ever going to, the only one that has horizontal asymptotes is arctan. The arcsine and the arcsecant don't. So the only one with horizontal asymptotes is arctan, which is why we see it so frequently. Because the other functions aren't defined for all x's. Right. If you look at the other arc functions, they're limited. So arctan is going to show up a lot because of that fact that it's got 2 horizontal asymptotes.
So if we get arcsine or arcsecant, it won't make this.
It depends on what the limits are. But in general, we're going to see a lot more of this because the arctan function has limits at infinity, where arcsine and arcsecant don't have limits at infinity. Yeah. Yeah, so finite area right there. Finite area. Yeah, questions?
So like from the previous example that diverges, it gives us, it's going to infinity. Are we going to get a situation where it's going to be like infinity minus infinity?
Well, it can't be infinity minus infinity because it's all above the x-axis.
Okay.
So it's got to be positive. Oh. Right, so both of those have to be positive.
And so if it's a situation where it's like infinity plus infinity, that would just be infinity.
Yes,
right?
yes, still diverge.
Okay.
Yeah, as long as one side diverges, the whole thing diverges.
Infinity minus infinity, what's that?
Indeterminate. Could be 0, could be 1, could be 100, could be infinite. Depends on how fast each of those things are going to infinity.
Aleph 1 minus Aleph over.
What if it's 2 times infinity minus infinity?
Don't know, it's indeterminate.
That's still the same.
It's indeterminate, yeah. Yeah, you know you start getting into that sort of sizes of infinity, and the smallest infinity is the one that's countable, like the natural numbers, that's infinite, 1, 2, 3 goes on forever. But then if you look at the real numbers have a bigger infinity than the
But it still doesn't
counting
matter,
numbers.
'cause it's just infinity.
It matters in a different class. Doesn't matter in this class.
Different math class or different?
Different math class. Different math class.
No, it matters in English, guys.
It matters in psychology.
Physics for engineering, smart ass.
Physics for poets. Okay, so here's another one where the denominator is a power of 2. We've already seen that if we had 1 over a power of 2, that converged, that went to 0 fast enough. So the question is, what do you think here? What's your intuition here? Do you think this would converge or diverge? Think about,
Converge.
so we heard converge.
Yeah, I think that was what I said in this one.
Wow, what intuition.
So it's, okay, so it's, well, it helps me determine whether or not I actually want to do the math.
What do we think? Does anyone think it could
Like,
diverge?
if I can look at the graph, then you
No, it's going towards the line too fast.
So think about the numerator. The numerator is trapped below pi over 2, right? So the numerator is acting kind of like a constant. It's not growing above pi over 2, but the denominator is growing without a bound. The denominator is getting as large as you can imagine. You know, as x gets bigger, the denominator gets bigger, but the numerator is sort of staying constant when you get way out on the x-axis. So our hunch is that it should converge. Because the numerator is constant. If the numerator is acting like a constant, this is sort of like a constant times the integral of 1 over x squared. And we've already seen that 1 over x squared converges. So 1 over x squared converges, and this is just like multiplying by a constant. that 1 down there that's not going to do anything. That's going to be insignificant when we start letting x go to infinity. So our intuition, and if we look at the graph right there, yeah, it looks like it's going to the x-axis very quickly. So our intuition is that it should converge. Let's do the math. So let's do the math. So we're going to take the limit as b goes to infinity of integral 1 to b. So what we're doing is creating a definite integral. We're saying let's chop it off right there. We're going to get the area of this definite integral from 0 to b. That's going to be a function of b. That will be a function of b, FCN function of b. And then we take the limit as b goes to infinity. So we are sitting in this position. Now we have to integrate this. And what technique of integration seems like it should work?
Integration by parts.
No.
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 Sorry.
Substitution. Remember, substitution you always want to go to before you get to integration by parts or trig sub or anything. And integration with substitution, if the derivative of one of the functions is in the integrand, then substitution is probably the way to go. And when we look at the numerator, the derivative of the numerator is 1 over 1 plus x squared. So we see the derivative of arctan right there. So let's go ahead and try it. So we're going to let u equal arctan. If we let u equal arctan, then du is going to be 1 over 1 plus x squared dx. Perfect. So that works out perfectly. This is just going to be limit of, that's just u to u. Integral u to u. And let's not find these limits. We'll come back to the originals, so we'll just use some placeholders. Jeez. Placeholder limits. So we will end up with limit of u squared over 2, 1/2 u squared. Placeholders for now.
Can you put a star underneath the limit because the limit's changing because now we're no longer in terms of u, in terms of u?
Yeah, you could. You don't need to though, because it's just going to be sort of an intermediate phase here, and then as soon as we get back to x, then it will all be copacetic.
Okay.
So this will be arctan of x quantity squared. And now we have our x limits of 1 and b. Do not write that as tan to the negative 2.
If you change the limits of x to u, wouldn't it just give you normal numbers and then you just do it like normal?
Yeah, quite frequently. In this case, it does. Because we can evaluate that pretty easily. Arctan of 1 is
Pi over 4.
pi over 4, and then arctan of b would just stay arctan of b.
But you could put infinity in and then you'd get pi over 2.
We can't do that yet.
Oh.
We have to evaluate we have to find this function of b before we deal with that limit.
Okay.
So that's why it's usually better not to. In this case, you could, but you would have to write it then as pi over 4 to arctan of b, which, yeah, right there, you could. But usually with improper integrals, it's just easier to go back to the originals, almost always. So then here, we'll pull out the half, and we're going to have limit and our limit subscript. Now I'm going to put it back in, because now we're going to use it. So this is going to be arctan of b quantity squared minus arctan of 1 quantity squared. And we're taking the limit of all of that. we've already seen earlier today, you've seen it a lot this semester, arctan of b, as b goes to infinity, that's going to be pi over 2. The arctan function approaches pi over 2. So that's going to be 1/2 multiplied by, so pi over 2 quantity squared. So that's going to be pi squared over 4 minus, oh, this part's a constant, right? Arctan of 1 is pi over 4, and then we square it. We're going to get pi squared over 16. So then we get a common denominator of 16. So we multiply this one by 4 over 4, so we get 3 pi squared divided by 32. No, yeah, 32. Multiplying by 2. So that is the area, which means it's finite. The area is finite, the integral converges. All right, any of that you have questions on?
Is there a largest possible finite area value?
No. Yeah. You can create a function that has an unbounded tail that will converge to any number you want. Yeah. Everyone evaluating okay? Plug in the b, arctan of b, arctan of 1. Arctan of b, as b goes to infinity, the arctan function goes to pi over 2. Then we square it, so we get pi squared over 4. Arctan of 1 is pi over 4, and then we square it, so we get pi squared over 16. That all makes sense? All right, so it's finite. Finite, finite, finite. Gabriel's horn, so we'll take our break in a minute, but let's talk about Gabriel's horn first, so you can think about it during the break. So Gabriel's horn is found by taking the function 1 over x and rotating it around the x-axis, creating this unbounded horn. So out to the right, unbounded. We are going to show that Gabriel's horn has finite volume, but infinite surface area. Finite volume, infinite surface area. And so there's something called Gabriel's paradox that says this. If the horn has finite volume, you can fill it with paint. But if it has infinite surface area, it can't be painted. But if it's filled with paint, it's painted. So how do we resolve that paradox? That's what you need to think about during the next 10 minutes.
Doesn't that defeat the purpose of the paradox?
Think about it for the next 10 minutes.
Oh, okay.
So it's got finite volume, infinite surface area. If it's finite volume, you can fill it with paint. But if it's infinite surface area, it can't be painted. But if it's filled with paint, it's painted. So think about that. Think about how we can resolve that paradox. Let's continue on with Gabriel's horn. Let's first show that we do in fact have finite volume and infinite surface area, and then we'll talk about resolving that paradox. So the function that we are going to deal with is 1 over x. Its derivative is minus 1 over x squared. So here is the equation for volume. Do you agree that we're dealing with cross sections that are disks? And if we draw that element right there at x, if that rotates around the x-axis, it's creating a disk. So with the disk method, we will do pi times the radius squared. That's going to be the area of the disk. The function is creating that radius. The radius is right there. And so the radius is the function. So the radius is 1 over x. So pi times radius squared is going to be pi times 1 over x squared, which gets us to that point right there. So there's where we're at. All right, we turn it into the limit of a definite integral. So this is going to be the limit as b goes to infinity. We can integrate this. We add 1 to the exponent. We divide by the new exponent. We go 1 to b. So no funny business yet. We can factor out the constant to the front, negative pi. And then we have limit as b goes to infinity of, so the negative pi came out. So we have b to the negative 1 minus 1 to the negative 1. So that's 1 over b minus 1 as b goes to infinity. So the constant all came to the front right there. And then 1 over x. Plug in the b to 1 over x and get 1 over b. Plug the 1 into 1 over x and get 1. And what is that limit?
-1.
So the limit of this piece right here is -1, because 1 over b goes to 0. As the denominator goes to infinity, the fractions go to 0. -1 times pi gives us pi. So this is the volume, pi cubic units. So that shows us that the volume is, in fact, finite. So showing that the surface area is infinite, we know our surface area formula. So the surface area formula, we do 2 pi r. So we're at 2 pi r, that's the circumference, 2 pi r. R is 1 over pi, just like it was, 1 over x, just like it was there. So 2 pi r. And then we know that the ds, so all of this right here is ds. And ds is the square root of 1 plus the derivative squared. So 1 over x is the function. Its derivative is minus 1 over x squared. This becomes 2 pi r times ds. And again, ds is the square root of 1 plus f prime squared. So 1 plus 1 over x to the 4th. All right, now that integral is not an integral that we can evaluate at this point. It's really hard. So what we are going to do is something kind of clever. We are going to say that this quantity here, if we focus on what's inside, we are going to say that this integral here is more than the other integral on the other side of this inequality symbol. So focus on those two things. So do you agree that what's in this square root is more than 1? Right? That square root is of 1 plus 1 over x raised to a power. So this right here is bigger than 1. Any disagreement with that or any questions on that? Make sure you can see the x to the 4th. So that's more than 1. So if we take away a piece of this that's more than 1, we're going to be left with something smaller. Everyone agree with that? If you have two factors that are multiplied together, let's say 2 and 4. You take away the 2, right? You're taking away the 2, then you're going to create something that's smaller. If you take away a factor that's bigger than 1, you're shrinking the quantity. So this is true. This integral right here is where we're trying to evaluate. If we can show that this integral is infinite and this integral is bigger than it, then that has to be infinite also. So that's our logic. So let's take a look. So right here, this limit of, why is it doing that so much today? So we are going to take this integral, 2 pi 1 over x dx. So this is going to be the limit of 2 pi, isn't the integral of 1 over x natural log absolute x? So we can pull out the 2 pi, integrate 1 over x. This is going to go 1 to b. And I'm going to pull the 2 pi out in front of the limit symbol. And then we're going to have the limit of natural log of b. B is already positive, so I don't need the absolute value. Minus natural log of 1. And this is as b goes to infinity. And what is that limit?
Infinite.
Infinity minus 0. So that's infinity. Infinity times 2 pi is still infinity. So this limit is infinite. So therefore, we have infinite surface area. So infinite surface area. Jose?
Don't know if it's related, but do black holes work like this?
I have no idea. That's a good.
Okay.
Find out and let me know. If we can figure out how a black hole works.
Because I've seen some that are just like, you know, and I
Yeah.
don't know, it looks so.
Rose saw a black hole. Wow.
Yeah.
High definition.
You'll just
Mm.
it's infinity because it's
HD vision.
Oh, we got the.
We will.
5K.
We will get to that.
I can
point.
see like three
It's not a
separate
harmonic
ones.
series here yet.
And there's
because
birds
it's
are like,
continuous.
there's Alpha Centauri.
So,
Still doesn't stop
yeah, we're gonna
from
get to
failing.
that point where we look at it as
So
a
the
series.
surface area on this thing is just, is infinite because the length of the curve itself is infinite, because it never truly reaches 0. But the volume effect really becomes 0. So here's the thing. Actually, if it's 0,
Isn't that what Newton did?
that means you have an infinite curve, which involves
You can get finite surface area with an infinite curve. You can get finite surface area. If you integrate, if you take the curve 1 over x squared and rotate it around, you'll get finite surface area. What the piece that matters is this. The piece that matters is what you end up with in the denominator of the integrand. Like here we ended up with an x to the power of 2. X to a power of 2 goes to 0 fast enough, 1 over x to the 2 goes to 0 fast enough that this is going to be finite. Here, if you were to look at the denominator here, the square root of x to the 4th is, this whole thing here is going to create, let me see if I can explain it in a concise way. If we look here, this denominator is not going to grow fast enough. This is going to be infinite because the denominator is not growing fast enough. So the effective denominator over here is 1 over x. And so that's not going to be fast enough in its path to 0 to create convergence. But you can have you can have a curve like 1 over x squared rotated around, and it will have finite surface area. So it all depends on what you end up with in the integration. And it turns out with that curve, you'll end up with something that goes to 0 fast enough. So it's not as easy as saying, oh, the curve is infinite surface, or infinite arc length. Infinite arc length rotating around is not enough to be finite or infinite. All right, so here we are concluding infinite surface area. So how do we resolve that paradox then?
Is it because volume is like the inside, but surface area is outside?
Not exactly, because the thing is, the horn is paper thin. So if the inside of the horn is painted, we would say it's painted. But is the inside really painted?
How can you tell?
Well, if that funnel goes on forever, like in your mind, when someone says, how much area can you paint with a can of paint? That's completely based on the diameter of a particle of paint. Right? And so if we have our can of paint and we can paint a big disc, use up all the paint, if we let the diameter,
go smaller than the
Here's-
size of a molecule of paint.
Yes, so if we let that diameter start to shrink, then we can paint bigger and bigger discs. And so technically, from a mathematical point of view, you could paint an infinite surface with a finite amount of paint, just wouldn't be very bright. So that paint's going to be you'd have to shrink it down so low that it's going to be very faded.
It's be like a mist.
Yeah, it's going to be a mist. It's going to be a misty. But
It's
so
painted,
that's
but it's invisible.
it's invisible paint. Yeah, exactly. Yeah, so but that's how they resolve it, is that our concept of paint is different than our concept of infinity. Caitlin?
For the Gabriel's one, will we have anything like it on the test, or just for wanting to?
You will have to find volume of something on the test, yes. No paradox, though. Caitlin's paradox. It's got finite surface area but infinite volume.
Okay, that's just.
Is that
creepy.
possible?
No. That's a true paradox. Yeah, we can't, yeah. You'll see all these things that have like infinite surface area, or infinite perimeter but finite area, infinite surface area but finite volume,
Where do fractals fit in these?
right in the middle.
Right in the middle.
Yeah, all those things are fractal. Like if you look at, when we do the Koch snowflake, which we're going to do in the next in the Infinite Series chapter,
Okay.
the Koch snowflake has a fractal boundary. And so that's what creates the infinite perimeter. Yeah. All right, so let's try this one. So this says, take this curve and rotate it around the x-axis and find the volume. No, it doesn't say find the volume, just find the area, I guess. Yeah, region bounded. So find the area. Okay, so when we look at that, what do you, oh no, it does say revolved around the x-axis. So yeah, we're finding, oh, volume up here. I was looking in the problem itself and I didn't see the word volume. Yeah, we want to find volume. Okay, so this is going to rotate around the x-axis. It's also creating a funnel-y thing. But it doesn't look like that is going to the x-axis very quickly. So it feels like this probably will have infinite volume because it's not decreasing quickly enough. Well, let's check. So once again, we are going to rotate around the x-axis. We're going to use the disk method. So we have, that scenario kind of set up. And the area of a cross-section, the area of a disk, is going to be pi times r squared. And r in this case is the function. So it's going to be pi times r squared. R is this crazy looking function. So that is the function we need to integrate. So to find the volume will be the integral from 0 to infinity. We know we're going to need to use an improper integral technique. So we're going to have the integral from 0 to b. That's a definite integral. And we are going to integrate pi times that squared. So that's going to give us x divided by the quantity x squared plus 1 to the 2/3 dx. So, what technique of integration do you think we should use?
Substitution.
Yes. Wow, good. Very good. So let's let you, I'm surprised I didn't hear trig sub. So we're going to take the denominator quantity and we're going to do that. Over there inside we have a dx times x, so let's isolate dx times x. So we will have, let's see, pi all the way to the front. So we have the integral u to the 2/3 in the bottom. That's going to mean u to the negative 2/3 in the top. And then x dx is du divided by 2. du, and we'll put our division by 2 out in front. Now these are going to be u limits, so we're going to go ahead and just wait, and we'll come back to x in the end. So substitution works beautifully here. We're going to do our power rule for integration. We still have limit. So we'll have u to the 1/3, adding 1. Add 1 gives us a third. Dividing by a third gives us multiplication by 3. And these are still with some placeholder limits. Then we'll pull out the 3. We'll back substitute. We said that u is going to be x squared plus 1. And x is, let's see, b is going to infinity. And this is going 1 to b. So now we're back. Back to x limits. We're going to just drop in those limits of integration, nothing too complicated yet. We're going to take the limit as b goes to infinity of b squared plus 1 to the 3rd minus 2 to the 3rd. Take the limit of all of that. And what is that limit?
2 to the 1/3. Minus 2 to the 1/3.
Nope.
Infinity.
Infinite? So this part here, as b is going to infinity, we have a 1/3. So like always, that's a bird wing. Fractional exponent, bird wing, as we go to infinity. So this is going to infinity. Infinity minus a tiny constant is still infinity. Infinity multiplied by a positive constant is still infinity. So positive infinity.
Isn't the lower limit of integration 0?
Oh, did I go to 1? Oh, yeah, it should be. Oh, thank you. Yes. Good call. So it's going to be even less than infinity. Oh, no, it's still infinity. Good catch. So that is a 0. Good catch.
It's still infinity.
It's still infinity.
But you'd mark us down for that, wouldn't you?
Yeah, definitely. All right, so that's infinite volume.
So infinity to a positive value is always infinity, and to a negative value is always 0.
Yeah.
What if it was 0?
Infinity to the 0?
Is that 1?
That's indeterminate. It could be 1, it could be 10, it could be 0.1.
What's the value on that?
Well, you have to, if you have infinity to the 0, you have to just use one of those techniques from Calc 1 to do the evaluation, like a log limit type thing. We'll do that later, actually, in the next. I forget if it's this chapter, but we'll do that soon. So you have to do log limit stuff. Yeah.
On,
Log
like
limit.
a test, would you want us to say like a divergence?
No, not in this chapter. It's fine if you just say infinity. It's totally fine. When we get to infinite series, you'll use that terminology. Infinite series. All right, let's go the other direction.
Will it always?
Vertically unbounded.
Will divergence always go to infinity or negative infinity?
No. Yeah. In this context, yes, but in big picture, no. When we talk about series, they can diverge by oscillation also. So they can diverge by this method or by oscillation. Question? The pi over 2. That came from this pi. I've got to go back.
So you would say like something like the sine function diverges as well?
This, hold on 1 second. So when we do the substitution right here, du over 2, this x dx becomes du over 2. So there's the du and there's the 2. Make sense? Yeah, the sine function does not converge. It diverges by oscillation. Yeah. Okay, so now let's do the other way. So these ones are more sinister because you don't see them. When you look at this integral, there is no red flag. With the horizontally unbounded regions, you see the infinity or you see the negative infinity and you instantly know, oh, improper integral, I've got to write down limit. Here you don't see it. And unfortunately in Calc 1, you sort of, every time you saw a definite integral, you just started integrating. And you didn't pay attention to the limits until after you did the antiderivative. Here you've got to be a little more careful. Because if the function is not defined at one of the endpoints, then you can't just integrate it. Right? So we're going to do something similar to what we did before. We're going to introduce a definite integral. So we're going to integrate from c over to b. And this is going to create a function of c. And then we're going to let c go to whatever that asymptote is.
So how, does this mean we need to check this every single time because like?
I mean, you're going to know because on this test it's improper integrals and you're going to know.
I know, but like
In general, you should think about whether the function is defined on the integral. In general, you should.
Okay.
You should.
But you wouldn't like try and.
No, I'm not going to try to sneak one out. I'm not going to try to sneak one on you. No. So the idea is similar. Here we have unbounded on the right side. So we're going to approach A. Now this is important that we approach with a one-sided limit. Right? This limit is as C goes to A from the right. Right? That's important. We want to stay within our region. And here, if the asymptote is on the right-hand side, this will be as C approaches B from the left. Right? So we're coming into B from the left. So when you do these vertical ones, it's going to be important that you put a one-sided limit there. And then two-sided limit, same idea as before. We have to figure out the left side, figure out the right side, and then add them together. And if one of the sides is infinite, then the whole thing's infinite.
Let me scroll to the top a little.
Okay, so let's try one of these unbounded vertically ones. So vertically unbounded regions. Vertically unbounded. So here, we're going from 0 to 1. So our x value right here is 1. And we are trying to find this area here, this vertically unbounded region. We already know the horizontal region is finite. We already showed that. 1 over x squared, horizontal is finite. And you can kind of see that the graph pinches that x-axis really quickly. And you can kind of see that the function is pulling away from the y-axis. It's not nearly as tight. So just by looking at it, we're thinking, I wonder if it's going to be divergent. So let's check. So from 0 to 1, we are going to first, so when you look at that, it's not obvious until you think about the limits that this is improper. Right? 1 divided by 0 is undefined, which is not something you normally had checked in Calc 1. You just were given integrals where the function was defined at the endpoints. So we know there's a vertical asymptote there, so we have to create a definite integral. So we're going to let C go to A. A is 0, so we're going to go to 0. And you're going to tell me whether we should go from the left or the right.
Left.
Right. Thank you. So if we think about our interval, 0 to 1, 0 to 1, we're approaching 0 from inside the region. We're coming into 0 from the right side of 0. It is the left endpoint of that interval, but we're approaching that left endpoint from within inside the interval. So we're coming in from the right of 0. And then we integrate this. This is easy to integrate. We add 1 to the exponent, divide by the new exponent. And this will be from c to 1. And then this will be limit of, plugging in the 1. 1 to the minus 1 is just 1. And then there's a minus 1. Minus a minus is plus 1 over c. And this is as c goes to 0 from the right. Okay, so what does that limit? What's the limit of -1?
-1.
-1. So now we're trying to evaluate the limit of 1 over c. C is not going to infinity, though. It's going to 0. So the denominator is going to 0, which means the fractions are getting bigger and bigger and bigger. Right? As the denominator gets smaller, the fraction values get bigger. Think about 0.1, 0.01, 0.001. So they're getting huge. But notice that the denominator is always positive because we're approaching 0 from the right. So the denominator is always positive, so this is going to positive infinity. Subtract off 1, we're still going to positive infinity. So this is going to go to plus infinity. So diverges vertically. So now we see that with 1 over x squared, we have divergence vertically, convergence horizontally. And this is going to be a pattern that we will see. It's kind of like a whack-a-mole. As your function gets closer to x, it's pulling away from y. If we created a function that gets closer to y, it's going to pull away from x. So we're going to see that we're going to have convergence on one and divergence on the other in all cases but one. We will get to that single case. All right, so any questions on the math there? All right, let's try another one. So let's do this function, 1 over x to the 1/4. This horizontal tail looks pretty bad, but the vertical tail looks pretty tight. Right? Now notice the power in the denominator. That power is 1/4 in the denominator. We showed that 1 over x squared was a convergent horizontal. This is not going to grow, depends on how you look at it. The denominator is not going to grow fast enough for the fractions to go to 0 fast enough. Okay, 1 over x to the 1/4 is going to grow very slowly. So this is not going to converge, it's going to diverge. So you can think of it in two ways. These fractions approach 0, but they approach 0 slowly. Or you can say, focus on the denominator. This denominator goes to infinity, but it's a bird wing. It goes to infinity very slowly, which means the fractions go to 0 slowly. So you can think of it by either looking at the denominator or looking at the whole fraction. It kind of depends on what's best, in a given situation. All right, so that one we're going to see is going to converge. Excuse me, that one we're going to see is going to diverge, but this one will converge. So if it converges vertically, it's going to diverge horizontally, and vice versa. So let's show. Let's do the math here. So this is going to be the limit as c goes to 0 from the right. And again, we're just going to rewrite this as x to the -1/4. And this is going to be c and 1. So this will be the limit. We just use the power rule. So that's x to the 3/4 divided by 3/4 is a multiplication by 4/3. So we have that. So this will be 4/3 limit of 1 minus c raised to the 3/4 power. And that's as c goes to 0 from the right-hand side.
Did you forget the dx?
Oh my gosh!
No way.
-1. Thank you. Oh, I didn't even take off last test for that. I'll take off next test.
Wow.
Okay, so what is that limit equal to? So the c to the 3/4 will be 0. The limit of that is 0 because we're plugging in 0, and that's in the numerator. Unlike the last one where the c was in the denominator, so we got an infinity. So this is going to end up being just 4/3. Finite, yep. So vertically, we're going to have finite area. So we're going to 1 right there. So this area right there, I mean, obviously it goes up forever, it doesn't stop, it's unbounded, it's just, can't see it graphically. So that is going to be finite. And this one will be infinite. So if we wanted to just confirm that this is going to be infinite, we are going to let b go to infinity. We're going to integrate from 1 to b, x to the minus 1/4 dx. So that's x to the 3/4 times 4/3, 1 to b. 4/3 comes out, limit b to the 3/4 minus 1 to the 3/4 is just 1. And this b is going to infinity. So what is that limit as b goes to infinity? B to the 3/4, 3/4 creates a bird wing. As b goes to infinity, infinity, infinity minus 1 is still infinity, infinity times 4/3 is still infinity. So we're going to see this commonly, that converge vertically is going to mean diverge horizontally.
So
And vice versa.
C, as it approaches 0, becomes infinitely bigger,
Mhm.
right? Then why doesn't that resolve to negative?
Which one are we looking at, the left or the right? Where are we looking? Here?
Left.
Left, okay. And say that again.
If C gets infinitely bigger, why doesn't
C is going to 0.
What I'm saying is, like, as C approaches 0, from
So
the right side.
I think I know what you mean. So if we look at this function right here, there's the function, c to the 3/4 is a bird wing, but we're going to 0. So the function, as c goes to 0, the function value goes to 0. We're not taking the limit as we go to infinity. The limit of this as c goes to infinity is infinity, but the limit of this as c goes to 0 is 0. So this is a picture of y equals c to the 3/4. I should write it as x to the 3/4. So that's a picture of x to the 3/4, and as we go to 0, the function value is 0. If we go to infinity, the function value would be infinity. But if we go to 0, the function value is 0. Let's try another one. So here's one that's a classic that it is totally not obvious. It's not 0 at either. It's not 0, or we don't see infinity in the endpoints. But if you plug in an endpoint, you get division by 0. So it's not obvious, but if you check your endpoints, you check -3, you plug it in, you see you've got a vertical asymptote right there at -3. So we've got this vertical asymptote right there. And so the question is, if we integrate from -3 to 1, so on this blue segment, is that area finite? Is it infinite? And so we're going to set it up as a vertical problem. So this will be the limit as c goes to -3 is the bad endpoint, so that's the one we're approaching. And are we approaching it from the right or the left? From the right. We're coming into -3 from the right side. So we'll have that. And then c over to 1. So here's where we're creating this definite integral. So c, we're just imagining c right here. We're finding this area right there first as a function. That'll be a function of c. And then we'll take the limit of that as c goes to -3. Okay, well, we've seen a ton of these. All we do, anytime we have an exponent in the denominator, we're going to pull it up to the numerator and integrate it with the power rule and reverse chain rule, possibly. So we'll have limit. Integral of that's going to be 2x plus 6. Add 1 to the exponent. Get a third. Divide by a third means multiply by 3. Reverse chain rule says take the derivative of the inside and divide by it. Say if you have any question on that. So then we're going to factor out the 3 halves, plug in a 1, looks like 8 to the 1/3, minus the quantity 2c plus 6, all raised to the 1/3 power. So the 3 halves is coming to the front. Factor that out. Then we plug in a 1 for that x. That's 8. Third root of 8 is 2. And then we subtract off, plug in a c right there, so we get 2c plus 6 to the 1/3 power. And we want to know what the heck happens as c goes to -3 from the right. Okay. Limit of 2 is 2. Come over here, we start plugging in -3. And what do we get? 0. So we're good. And we don't really have to think much about the plus in the exponent there, because we're getting 0. Like you already know from Calc 1, if you take that limit value and plug it in and you get a number, you don't even have to think. You just write down that number. If this function is continuous, if it's defined at that value, all you have to do is plug it in. You don't have to think twice. That prior one, we had to think about when the denominator was positive or negative, it was going to 0. We had to figure out what the sign was. Here, if you plug it in and get 0, you're done. You don't have to think. So -3 goes in, 6 minus 6 is 0, that's gone. Limit here is 3. Therefore, we have convergence. So that tail, so this whole vertical, we're finding not to the right, we're finding this here, finding all of that. So all that's going to be finite. So let's think about the effective power on the x value in the denominator. What's the effective power down there on that x? 2/3, thank you. The effective power is 2/3. That is less than 1. So we've seen so far that when the power is less than 1, we have vertical convergence and horizontal divergence. If the power is less than 1, you can kind of see from the picture it's closer to y than it is to x. If we were to do the x direction, if we were to do from -3 to infinity, not negative, if we just did from 0 to infinity, it would be infinite. So fractional x, finite vertical, infinite horizontal. And if we had a power bigger than 1, like we've seen 2 and some other powers, finite horizontal, but infinite vertical. So we're going to get to a point where we're going to conclude, we're going to make the conclusion in a second. Almost there. Almost somewhere. So let's take a look at this one. So here's another vertical one. It's a little harder to kind of gather what the effective powers are at this moment. We'll think about it in a second. Let's first just do the math. So we're trying to find this vertical region. It's unbounded, therefore it's improper. Not totally obvious when we look at it until we plug in the exponent or the limit of integration of 0. We see, oh gosh, the denominator is 0 at that limit. That makes it improper. As soon as we know it's improper, we need to have a limit. So this limit is going to be as we go to 0 from the right. So we're going to come into 0 from the right. Integral c to natural log of 3. And what is our technique of integration?
Use substitution.
Use substitution. Thanks, Harrison. Harrison's favorite technique.
It works if it's not a group. As long as.
All these nested if-onlys.
Unfortunately, they're all roots, so.
What is this method anyway?
What's that?
What even is this method?
We'll see. All right, so everyone agree on this piece? If we let u be e to the y minus 1, its derivative is just e to the y, which is in the numerator, which is what makes it a perfect candidate for substitution. So we're substituting, so we're going to use some placeholder limits here. E to the y dy is du, so we're going to have u to the negative 2/3 times du. E to the y minus 1 is u. Pop that quantity to the numerator by switching the exponent to positive. And then e to the y times dy, that's all this right here. That becomes du. And then we've got a nice, friendly power rule. We will have u to the 1/3 times 3. Then we have to go back to our original variable. So u was e to the y minus 1. E to the y minus 1, all raised to the 1/3. Now we're back to our original limits, c and natural log of 3. Okay, let's see. So we're plugging in, trying to find that vertically unbounded region. So what happens when we plug in ln3? What do we get? 3. Everybody agree? E to the ln of 3, the e and the ln cancel, so we get a 3. So then 3 minus 1 is 2. So we'll end up with 2 to the 1/3 power, which is just a constant, minus, plug in c, what a mess. We get e to the c minus 1 quantity to the 1/3 as the second part. Now let's introduce our limit again. So that's as c goes to 0 from the right. And what is that whole limit equal to?
2 to the 1/3.
Does everyone see that if c is going to 0, the first thing we always do in evaluating a limit is plug in that limit value. Plug it in, and if we get a constant, we're done. We don't have to do any more analysis. So plug in there, e to the 0 is 1, 1 minus 1 is 0, so we get 2 to the 3rd times 3. So that means that the vertical tail is finite. It means that the integral converges. And that's the area. I just realized that I got a little overzealous with the yellow. We want to come straight down to that blue. So that area is finite. So that is finite. So then the question is, if we think about the effective exponent in the denominator, it's a little harder to analyze with exponentials, but we can still kind of get there. This is e to the 2/3 y, and that's e to the y in the top. So that's going to be, if we were to simplify that, what would we get? What would be the exponent? Is that where we are? What would be the exponent there? If we were to go up, so we have an e to the y in the numerator and an e to the 2/3 y in the denominator. So isn't that an e to the 1/3 y in the numerator? Right? So the fractions aren't even going to 0. So there's no way over here, right? This thing's going up, so you're going to have divergence over there. And if you were to bring it down into the denominator, you'd have e to the negative 1/3 y. So it's a little, you can't quite analyze it the same way as you can with x's, but you can see clearly why it's not going to converge down here, and the powers are going to be such that we're going to get closer to y and farther from x. What the effect of it's going to be. I mean, part of it is that with exponentials, let's not talk about it anymore. Really just depends on looking at a lot of examples before it starts making sense. Okay, so this one we're looking horizontally again. And we already know that if there was no ln there, we would have convergence. If we have 1 over x squared, that horizontal tail is going to be finite. We'll have convergence. If the numerator on x squared was a constant, we would have convergence. Right? We did arctan of x over x squared, and we got finite. Now we have a function over x squared. That function is going to infinity, but it's going to infinity very slowly, but it's still going to infinity. It's not going to act like arctan that's bounded. So this one's a little bit of a mystery. It's a tug of war between the numerator and the denominator. If the denominator goes to infinity way faster than the numerator, we will have convergence horizontally. That's what we have to find out. So let's try it. So we're going to use ultraviolet voodoo. So we're going to pick a u, and we're going to pick a dv, and then we're going to go from there. Okay, so natural log of x, the normal choice would be to put it right here in the u because we can differentiate it easily. All right?
Shouldn't that be a dv?
A dv?
Like next to the du, or next to the u?
Hold on one sec, let me just write this. Right here?
Yeah.
That's a dv.
Oh, okay.
That's a v.
U's look like V's.
Yeah, I don't put any tail on it when it's a v. It's so hard, this board is so finicky. So that's our dv, and that's going to be x to the minus 2 times dx. And when we integrate here, we get v equals, so we add 1 to the exponent, divide by the new exponent, we get minus 1 over x. Okay. So let's call this integral omega. Come over here, the original integral. Omega is going to be the limit as b goes to infinity, integral 1 to b of I guess I'm going to put a uv out in front first. So uv, so minus 1 over x, natural log of x, 1 to b. Now the integral part, so there's uv minus the integral of v du. V du is negative, so that's going to make this positive, integral 1 to b of 1 over x squared, which we'll write as x to the negative 2 dx. uv minus integral v du. So now we have limit. Let's do our evaluation all at once. Let's just be patient. So here we're going to integrate and get x to the minus 1 divided by minus 1, which is minus 1 over x from 1 to b. Whole thing from 1 to b. So this is going to be limit. Plug in the b for all the x's. So we're going to get minus, I'm going to write that as a fraction, natural log of b over b minus 1 over b. Minus a minus is plus natural log of 1 plus 1. So limit of all of this as b goes to infinity. Natural log of 1, what does that do?
0.
Yeah, that's going to be 0. So that's going to go to 0. How about 1 over b as b goes to infinity? Also 0? 1 over b? Okay. How about natural log of b over b? Let's come off to the side and do a little reflection from something you learned in Calc 1. So as b goes to infinity, minus natural log of b over b. This is an indeterminate form. The top is going to infinity, the bottom's going to infinity, we've got the minus 1, which doesn't affect it. So both numerator and denominator are going to infinity. What technique did you learn in Calc 1 for that indeterminate type?
L'Hopital's.
L'Hopital's rule. So you can indicate this in a couple of ways. You can put, L'Hopital's rule. You can, if you write this as infinity over infinity, like whatever you want to do to sort of indicate that L'Hopital's is coming into play here. So L'Hopital's rule is super intuitive. What we are saying is that we're taking a quotient of functions. Each function is going to infinity. What is the best approximation for a function? You learned in Calc 1, best approximation is the derivative, right? You've got your function, the tangent line gives you the best approximation at a point. The slope of a function is, by definition, the slope of that tangent line. And so what we're saying is that a quotient of functions is going to approach the same thing as the quotient of tangent lines, which makes perfect sense. Right? If the best approximation is the tangent line, the quotient of tangent lines should approach the same thing as the quotient of functions. So that's the nature behind L'Hopital's rule. So we take the derivative of the top, we take the derivative of the bottom, and reevaluate the limit. And what's that limit as b goes to infinity? 0. So this goes to 0. So that's an indeterminate form. Sometimes you get 0, sometimes you don't. It's indeterminate. That's why you have to do some further analysis. L'Hopital's does that further analysis for us. Okay, so that's all 0. And what is the overall limit there then? 1. 1. So therefore we have convergence. Therefore this tail is finite. All that for just 1. So let's think about our intuition that we're slowly refining. 1 over x squared converged. Natural log over x squared also converges. So natural log is going to infinity, but it's not going to infinity fast enough to upset the convergence of 1 over x squared. 1 over x squared is not being offset by that natural log. So we still have convergence.
Will you give us a similar problem to this on the test?
Yep. Okay, so let's look at our summary. So we're going to look at 3 functions here. The convergence threshold is the name of this slide. And this just summarizes everything. So first, let's look at the black curve. The black curve is 1 divided by x. 1 divided by x, so the power in x is 1. It's the black curve here. It's going to diverge in both vertical and horizontal senses. So 1 over x is our threshold. 1 over x diverges in both directions. If we look at the red curve is 1 over x to the 1.1. So we just bump the exponent a skosh over 1 in the denominator. And if we bump it over 1 in the denominator, looking at red, horizontally it gets tighter to the x-axis. It's going to converge. So if the exponent is just a skosh over 1, you get horizontal convergence. But notice as soon as that exponent goes a skosh over 1, horizontally it gets closer, but vertically it peels away from the y-axis. So we're going to get divergence there. It's even further away from the y-axis than the black curve, and the black curve already gives us divergence vertically. And the red curve's further away, so there's more area. So x to the 1.1 converge horizontally, but diverge vertically. And then the opposite is going to be true for 0.9 as an exponent. So now we're going to go a skosh under 1. If we go a skosh under 1, that's the blue curve. Go a skosh under 1, and it peels away from the x-axis, creating divergence. It's further away from the x-axis than the black curve, which already diverges. So horizontal divergence, but you bump that exponent down to 0.9, and it squeezes it into the y-axis, and so that's going to create convergence vertically. So an exponent less than 1 in the denominator, horizontal divergence, vertical convergence. And so that's what all this stuff is doing. That's what this is all saying. So 1 over x is going to diverge horizontally, 1 to infinity. It's also going to diverge vertically, 0 to 1. So 1 over x is the only function we see where we have divergence on both tails. The only function of this form, this 1 over x to the n form. So it diverges both directions. Bump the exponent, horizontal convergence, vertical divergence. Bump it down, horizontal divergence, vertical convergence. So that picture is a really good one to grasp. That's the good image in your head. If the denominator is growing faster than x, you're going to get convergence this way. If the denominator is growing slower than x, i.e. a fraction on x, x to the half, x to the 2/3, x to the 3/4, whatever, you're going to get divergence horizontally. And then vice versa for vertical.
Just curious, a test, if we knew something diverged and we could prove it, then could we use that as evidence that anything greater than that would also diverge?
Yes.
And you would accept that as an answer?
Yes. Yeah. That is legit.
So we could use those two notes as an answer.
You could use it as a justification for part of an answer. But you'd have to show what he just suggested. You can't just say, oh, this is bigger. You have to prove that it's bigger. So the question is, where do these things show up? And the most important concept that you are going to learn in differential equations is the Laplace transform. The Laplace transform is defined as an improper integral, and it is one of the creme de la creme types of topics that you'll see in DippyQ and in any engineering course. One of the things that you deal with in engineering is electricity, and electricity, most of the electricity we deal with is alternating. And when you look at the waves that build electrical currents, they are square waves. They are not differentiable, right? Because they have corners on them. And so what you can do is there's two things. There's something called a Fourier series, which allows you to build a curve that approximates curves that are non-differentiable really nicely if there's big gaps. A Fourier series can build a very tight curve around a step function. And then you get these Laplace transforms that can find area beneath curves that are not differentiable. So you can use a Laplace transform to change your function essentially to a function that you can do math on. So the idea is that you convert your function over to Laplace, you do math in Laplace, and then you convert it back to XY domain. So improper integration is not going to go away. If you're going to be an engineer, you're going to see lots of improper integration. So really important to sort of get a handle on it now before the stakes get higher. All right, let's stop there. I will see you all on Thursday.